All right, welcome to myself and John's presentation on Hitbox Performance for assignment 2 in 359, if memory serves. So let me start off with a few topics and then I'll hand it off to John. We have, first off, our software toolchain setup, and it's slightly convoluted, but it's also quite modern. We're using C++, and as a consequence of using C++ with other libraries like SDL3 and SPDlog, we're using CMake to organize all the libraries together and to manage our packages instead of trying to fiddle around with something like VC package or the aptitude repositories or whatever. We're just using Git submodules and we're building from source, so it's all statically linked except for SDL. That's a longer story. But as a brief intro to CMake for those who haven't seen it before, CMake is a tool that helps you build systems across platforms. So for instance, on Windows, it'll literally compile a bunch of Visual Studio projects that you can open up in Visual Studio and compile. And then if you're on Linux, it'll make a make file that you can just run make on. And it's slightly painful to use, but it does do the job quite well, and everybody on the planet supports it, so it just makes a lot of sense for us to use it. So we have a CMake file, and we're using other CMake files visible on our GitHub if you want to take a look. And we chose SDL because it's just easy to use. SDL3 is the latest one. It's developed and maintained by employees at Valve, if I recall correctly, and C++ because it's fast and lets us have a lot of control. And also, we both had some prior experience, so it's a little less of a pain point than trying to learn something weird. So I'll briefly cover spatial hash maps, and this is one of our main optimization techniques that we're using. So as an intro to this topic, games have this issue where they need to run a lot of collisions against a lot of other collisions. So in our not game, but demo here, you can see that there's many hitboxes. And in an actual game, like if you're playing something like Silksong, there might be even more hitboxes in game at once. So there's a few ways to go about optimizing all of that, but the best first step is often something like a quad tree or a spatial hash map. In this case, of course, it's a spatial hash map. And it's basically a grid. I've drawn it out here in the game, or the demo itself. I have it displaying the grid. Normally, you wouldn't see it in a game like Silksong or Mario or whatever, but I've drawn it out here so it's very clear what's going on. And we know we can just keep track of what cell anything's in. We have a slightly simplified implementation in our demo, but in the real world, what you would expect is every single one of these hitboxes would be in one or more of the cells, and it only needs to check for collisions inside the cells that it itself is located in. So for instance, this one here only needs to check for collisions in this cell and this cell, since these are the only cells it's in. So we know that anything in any other cell can't possibly be colliding with it. And that applies to everything here. So this just helps cut down on the total number of collisions. And it is technically a hash map. We store everything in a list, and then we index into that list through a hashing function. So this website has provided us with a great image demonstrating it. So this point here, we can check what cell it should be in, and in fact we do. So take this cell, for instance, you would take a point in this cell, divide it by the cell width and height, the floor of that, and then you would index the list by y times width plus x. So in this case, y would be 0, the width would be whatever it is, but it's not important because it's y is 0. So plus x, which is 2, 0, 1, 2. So we know it's the second cell. In this case, we have a y of 1. So we would add width to it, 1, 2, 3, whatever it is. And then we'd end up in this cell. It's just a very simple way of indexing a 2D grid into a 1D array with just one calculation. And it saves us on some weird 2D grid handling. And much more important than that, it saves us on cache performance. And our optimization techniques, as I just discussed, the spatial hash maps are very important. But another one we use is bounding boxes, because as you can see, we have very complex polygons, and we're using something called separating axis theorem to compute collisions between complex polygons, which John will talk much more in depth about than I will here. But just note that SAT, or separating axis theorem, is quite computationally complex. It requires a lot of processing time to do for any one collision relative to any given collision. So we use a much simpler bounding box collision, in this case, just a rectangle, which is an AABB collision. which is, I won't get too much into how that works again, but just know that it's four if statements. So we can first check if something is colliding with the bounding box, and then check if something's colliding with the actual polygon inside. And this is a great image to demonstrate that. As we can see, this one here, they do this in 3D all the time, where it's much more computationally complex to compute a collision with an object such as this than it is to compute it with a rectangle. So they just wrap the whole thing in a rectangle, and if these cube, and if this cube isn't colliding with this cube, we know that this polygon can't possibly be colliding with this shape, so we don't even need to check that. And it's just a way to cut down on the number of times we have to do separating axis theorem. And if you download and run our demo, you can try it with this optimization off. You can disable the bounding box pre-pass, and then you can see the huge difference in performance that you get. And of course, we have some information on that in future slides that John will talk about as well. So you don't have to take my word for it. We have some data to support it.
All right, now on to how the collisions work. So first I'll talk about AABB collisions, which are axis-aligned bounding box collisions. These are really useful for, later on you'll see, for performance, because we can draw a rectangle that is not rotated, but they all share the same axes, so they're aligned on the axes. It makes it really easy to compare whether or not they are colliding. So for the complex polygons, which I'll show after with SAT, it's really beneficial if you do a pre-pass check if the bounding box are colliding, because if they, like Paulo said, if they're not colliding, polygons can't possibly be colliding. So the way it works is just four simple if statements. Basically, x1 is the left, x2 is the right, y1 is the top, and then y2 is the bottom for the edges. So if any of these isn't true, then they are not colliding. So first of all, the right edge of an object must be greater than the left edge of the other object. The left edge must be less than the right edge. The top, y2 is the bottom. The bottom must be greater, because it's going down this way, than the top. And the top must be less than the bottom, keeping in mind that the y-axis ascends downwards in STL. And then we have a simple Boolean, which just checks this. All right, now on to SAT collisions. So this is much more complicated. So this is the separating axes theorem. Basically, to simplify it, you are checking if there is an axis in which two objects are separated. So for example, in this case, we can clearly see that there's no axes that they're separated on, because, no matter how I draw the axes, there's a collision. Now imagine if this triangle right here was translated like way over here, there would be an axis in the middle where they would not be touching. And that's what this is doing computationally. It's trying to figure out if that's the case. So how does it do that? So what it's doing is it takes the vertices, all vertices of the polygons, the convex polygons, and then it acknowledges how many there are. And then what it does is it draws edges for all of the vertices, and it'll translate that and then compare the other object and its min and max values along that axis and see if there's a collision. So for example, right, this edge right here, A1, between these two vertices, this gets translated perpendicularly over here. This is A1. And then we take the max value of the other polygon along this axis, which is this, and then the min, and then we do that for this object as well. And then we just see, using simple if statement, whether or not they're greater or less than in such a way that they would be aligned like this. That means there is a collision. The only case that there is not a collision is if you can find one of these axes in which they are not colliding. So in this case, obviously they are colliding in all of them. But what you would do is you would go for every single edge on both objects. So like here, 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 and you would just translate those, check all of them, and then you would have a case where there would not be a collision, like there would actually be a gap between these two along that axis. Here's the code for how we did that. Basically, we're just have the vertices for the object A and B, and we have knowledge of how many they are, like the length, and then we just check all of the edges. For the first object A, we do the perpendicular, then we do that as well for B, same idea, and then what we do is we check all of the axes for whether or not they overlap. All right, so now onto performance. You'll see there's a big difference between SAT and the regular bounding boxes on the aligned axes. So we use two different things that Paul talked about for optimization. First, we check, in the case of this one, we pre-check if the bounding boxes are touching, and then only afterwards do we do the SAT. It saves a ton of performance, as you can see, and then also the hash map, so that we're not checking every polygon against every other polygon. We're only checking them if they're actually close to each other on that hash map. And then here about timing and tech stack. So for timing, we have a loop that's going on. As long as it's true, the program will keep going. On false, it'll exit. During that loop, we take like the timing using STL, and then we compare how much has elapsed, and then we can average that over the entire time it's been running to get a good statistic for like how it's running. Another thing is we also allow you to change the modes. So we programmed it in so that it reads the keyboard each frame. And depending on what keys you're pressing, 1 to 5, it also shows it on the window header, like the title. You'll see that when I do the demo. You can go between all the different things and compare them. And then the window title does get updated depending on what collision mode you're on. Like if you're only on the bounding boxes, aligned axes, if you're doing both the bounding box and then the SAT check, or if you're just doing the SAT check. And there's also the ability to toggle the hash map. And then it just, updates the window all the time with that. So for debugging, the first polygon that's drawn is attached to your cursor. You'll see it in the demo, but it helped a lot for debugging. Instead of like, having to stare and wait for the polygons to hit each other, in good ways, you could just use your mouse and make them hit how you want to debug. And the way it does that is it just checks for the first box, the mouse state, and then it basically assigns your mouse position to the hitbox position. Project management workflow, we developed in the same repository. We were both implementing different features. Obviously for time, if we're both working on the exact same feature, it's kind of rough. And then we logged our progress through GitHub. You can see all the commits at this link here. All right, now for the demo. We're going to run it. You can see, like I talked about in the debugging section, we have a polygon stuck to our cursor, which is really nice for debugging purposes, instead of just waiting around and all that. So you'll see at the top here in the title, we have keys 1 to 3 change the mode, 4 and 5 toggle the hash map. So if I press 1, this is just drawing the bounding boxes. You'll see when the bounding boxes touch, it instantly turns red. And we have the SAT only, and you'll notice the timing here skyrockets, right? Bounding box only, SAT only, so much higher. Then we have the both together mode, where it does the bounding box first. So you can see, like, I can make it so that only the bounding box is red. A little scuffed. Only the bounding box is red. And you can see the performance is much better. We also have the hash map option. So pressing 4 and 5 on my keyboard, I can toggle it for any of the modes. It's its own toggle. And you'll see the performance so much better with the hash map for the SAT. And yeah, so the most performant would be to have both the hash map and then do the bounding box first and then do the SAT collision check. But yeah, really happy with how this turned out. Thanks for watching.